Okay, great. So now you've kind of know the very basic neural network, right? This is the feed-forward, fully connected neural network, right? And all these different building blocks, right? The neurons have different weights, bias terms, right? Those are learnable, and you also have different activation functions, right? You also have to specify a loss function, and with the training data, you're able to optimize these functions in order to have a very good function for the prediction in the inference stage. Okay. Next, we're gonna look at a particular neural network called convolutional neural network, CNN for short. And this neural network is widely used in image processing and computer vision. Okay. And for this class, right, because we are dealing with medical image processing, right, so you will see a lot of network basically using the convolutional neural network. Okay, so before we dive into the details about CNN, let's kind of give some motivations, right? Why do we come up with this kind of specific neural network design called convolutional neural network? So since we are dealing with images, right, some of the patterns are much smaller than the whole image, right? So if you look at this image, which contains a bird, right, as object, and for this bird, right, and we notice some of the, maybe we can call it very obvious or salient regions, right? This is the beak. So for human, right, if we can easily tell, this is a bird, and we look at like if there's a beak, right? So definitely we can have a very good educated guess, right? This is a bird. And if you look at this, very important features here, right? It only occupies a small region, right? If you look at this the entire image here, right? Maybe this could be like a 400 by 400 resolution, but this beak region only occupy maybe 20 by 20 pixels, right? A very small region. Okay. So if we still consider this fully connected, feed-forward neural network, right? Basically, it means every neuron is going to, connect with all the neurons in the previous layer, right? If we flatten the entire image as a giant vector, right? As we show that in the digit recognition example, right? So here we can still flatten this image into a large vector, and that's going to be your input layer, right? And if you're using the fully connected, right, the next hidden layer neuron, each of the neuron will have a connection with all these pixels, right? Let's say we have like a millions of pixels in these images, right? So each neuron, you have a million of connections with these input, right? Obviously, you can see how complicated this can be, right? You have a lot of ways to optimize, that's just one single layer, single neuron, right? If you have more neurons in one layer and multiple layers, you can imagine how many parameters for this particular mapping function, right? For the neural network. But for this particular case, a neuron does not have to see the whole image to discover the pattern, right? If I want to discover this is a beak, I don't need to see this background. I don't even need to see the wings and the tail and maybe the feet of the bird, right? I only have to focus on this small region. That's enough for me to tell or detect there's a pattern called the beak of the bird, right? So, kind of with this inspiration, right? If we only connect a neuron to a small region, and this will result in a very, much less parameters, right? So if we only, kind of naively crop out this small patch or region, right? And connect this with the neurons, as compared you connect the entire image to this neuron, there's going to be much less parameters in this case, right? So we can build this neuron as a beak detector, right? With less parameters. And the second observation is that the same patterns appear in different regions, right? Let's still using, this bird as an example, right? So we have two different images, okay? And maybe corresponding to different types of birds, but in general, we call this like a general category of bird, right? We don't consider this fine-grained classes. So if we look at the beak, right? If I build a beak detector, right? I can build this called like up left beak detector, right? So maybe in this case, this beak is appear on the up left of the image, right? But for this another image, this appear in the middle because of the position of the object, right? But no matter where the position is, so they all corresponding to the same pattern, right? It's just the position difference, right? It's on the up left, on the middle, or maybe even on the bottom or on the right corner, right? But they all corresponding to the same pattern, that is the beak of the bird. So you can come up with the like two different neurons, right? Maybe one neuron that is designed to detect the up left beak, but another one I can have detect the middle beak. Maybe I have a third or fourth one to detect beak at the different positions. But no matter how you can come up with different detectors, but they all do the same thing, right? They all detect the same pattern. It's just how the pattern appear, the position appear in the image are different. So I think the question is, can we just using the same set of parameters instead of you build like a separate detector, right? One set of parameter for this neuron to detect up left, and one set of parameter for this neuron to detect the middle. It's not necessary, right? We can using the same set of parameter in order to detect these beak, right? Maybe we just have to shift the neuron a little bit, right? Moving around this image so that with the same set of parameters, I'm able to detect beak appear in different positions. Okay, so that's the second observation. And the third observation is that subsampling the pixels will not change the object, right? So if again, let's look at exclusively on the bird image here. If we have this input bird here, right? We do the subsampling. Basically, we downsample, right? Into maybe half the size of the input, right? We have a smaller version of the image, right? Again, for human perception, right? We can easily tell, the main object doesn't change at all, right? So it's the same object, it's just, a smaller image size, right? So basically, for the machine, can be similar, right? So all these main information corresponding to the object still intact, right? So if we can do this kind of subsampling, we can make a smaller image, right? Which means that we have less pixel to process, right? And this will result in less parameters for the neural network to process, right? If we again consider the fully connected neural network, right? You basically cut the input neuron, think in this case maybe to a half or maybe to a quarter, right? So that's going to be a lot of saving in terms of the number of parameters. So in summary, we have these kind of observations or properties, right, from the images. So some patterns are much smaller than the whole image, right? And the same patterns appear in different regions. And if we do subsampling, it will not change the object, right? So the majority of the information is still gonna be there in the image. So based on these kind of property or inspirations, we can build this convolutional neural network by taking those property into account. So these are this very simple illustration, what this scene look like, right? So you have an input, you have a couple of basic building blocks, which is this convolution operation, you have the max pooling, and you can stack multiple of these kind of structure or layout, right? Here I have like a stack, another conv and max pool, but you can stack as many as you want, right? Maybe another conv and max pooling. And at the end, you do the flattening. So basically become a fully connected neural network, right? You can still connect a couple of layers and to before the final output layer to predict what type of object this image is. So for property one, right? So some patterns are much smaller than the whole image. And property two, the same patterns appear in different regions. And property three, subsampling the pixel will not change the object, right? For these two, the first two properties, right, it kind of inspired us to design this convolution operation. And the third property kind of inspires to design the operation of max pooling. So we'll look into these different, operations and how these able to kind of leverage these properties we observe from the image. Okay, so let's look at convolution, right? So for this example here, we have a much simplified example here, right? So we have a 6x6 grayscale image, right? Maybe they all have the pixel intensity or value 0 and 1, just for simplicity. Okay, and we have this convolution kernels or filter. Okay, so here I'm just made up a couple of filters. This one has the diagonal components all equal to 1, right? The off diagonal -1. Okay, so this more like a diagonal edge detector, right? So we have a large positive value on the diagonal case. So another filter or kernel is we have a vertical, right? Vertical have a positive value here. The neighbor is going to be like opposite, right? -1 here. So maybe this is like a vertical edge detector, right? So basically this is like a small matrix, right? And these are the network parameters to be learned. Okay, here I'm just make up a couple of numbers, right? Based on my maybe experience, I want to design such of the edge detection detectors, right? Act like edge detector for this filter. But in practice, all these filters can be randomly initialized and will learn based on the training data set, okay, and based on the objective function, right, the loss function you specify. So here, let's look at the first one, right? This diagonal has 1, and this is how it's operate. So you pretty much lay this matrix or the filter on this image, right? So on this first position, and you do this basically element-wise multiplication and sum them together, right? So the dot product of these two matrices, right? One is the 3x3 region, the pixels on this image, and the other matrix is your filter, right? The weights in the filter, right? You end up with a value of 3, right? You can do this, right? Well, this is 1 multiplied with 1, right? The other all 0. So whatever the number you have is going to be 0. So you end up adding the diagonal, right? Three ones together equals to 3. And you also have to specify the stride, basically how many like columns and later the rows you want to skip or jump towards the next position. So here we just specify stride 1, and we do the same thing, right? Do the dot product of these two matrices, and we get another value. Okay. So if we have a different stride, right? So before we have stride 1, right? So if we have a stride 2, which means we shift 2 columns here, then we go to here, right? So next position, you're gonna do this, matrix multiplication. The dot product of the two matrices is gonna be overlay here. Okay, so you get the idea, right? How we can slide this filter across the entire image, right? You just think of this as like a flashlight, right? The flashlight on the wall, right? You have a region, and you kind of moving that flashlight across different rows and columns. Okay, you generate these values. Okay, so basically I'm gonna basically kind of repeat, right? Column by column, row by row, right? You end up with the last position here, you end up with this so-called feature map. This is again a matrix, right? After you apply this filter, you generate this feature map. Okay. So as I mentioned, right? So this is more like a diagonal edge detector, right? So if you look at, right, usually if they detect similar patterns, right? If there's a diagonal have the similar, values on this image, will generate a large response, right? So here you can see that the first position here, which actually is the similar pattern, what this filter can detect, right? The diagonal edge, you can see it generates a large value, 3 here. But if you look at here, right, we also have a similar pattern on the bottom, right? And also you see there's a large kind of response here, right? 3, right? So, and this kind of related to property 3, right? Property 3 means, similar patterns can appear at different, locations of the image, right? We can using the same set of parameter or filter to detect these patterns, right? No matter the position, right? So we are able to detect that. And so this is just the one thing filter we generate this feature map. All right, we can specify another filter, right? So in this case, we have this vertical like edge detector, right? Before the first one, we have the diagonal, edge detector, right? So we can do this again, right? The same process, we can generate another feature map, right? Which is, indicated as the blue color, okay? So if you have more, like 3, 4, or even 10, hundreds of filters, then you generate the corresponding number of feature maps, okay? And notice that the input is 6 by 6, right? Here we have reduced the size of 4 by 4, right? Because we have a straight one and we don't have any padding around this original image, right? Because the filter has a specific size. So there end up have a reduced size feature map. So this is a very cool kind of animation, right? Basically illustrate how this convolution works, right? You can slide a filter or convolutional kernel, right, across the entire image and generate the corresponding feature map. Very simple. Okay, as I mentioned, right? So if we don't do any padding, then you may end up with a reduced sized image. But sometimes we want to keep maybe the feature map size consistent, right, across different layers for easy of the computation or interpretation. So to achieve that, we can do some padding, right? So here we can adding if we consider zero padding, right? So we can adding zeros, right? Like on these the borders, can say that. So this is a zero padding. You're basically adding zeros. We can also do mirroring, right? So you can mirror the same value here, 1, 0, 0, right? So you can also do maybe other type of value, like a mean padding, right? The mean value of the entire image and pad it here, doesn't matter. Okay, so in this case, you will get exact the same size of the original input. So that's the padding process. So for the color image, right? So we have different channels, right? So maybe we have 3 channels. Then here for the filter, we also have to consider different channels, right? So we have filters with 3 channels here. Okay, not just spatial height and width, but we also have the channel to kind of match the input. Okay, we don't have much time left. Then maybe we can look at this animation again, right? So if you have multiple channels, and this is like the animation it will do, basically slide across, different channels to generate a feature map. Okay. Okay. Yeah. So this slide pretty much kind of summarize, right? So if you have an input, spatially 32 by 32 with 3 channels, and you should make the filter. One thing to be careful is you have to match the channel size dimension, right? You have a 3 for the channel dimension for your filter, and if you specify 6 filters, right, you generate an image 28 by 28 by 6, right? Because each filter will generate a corresponding feature map, right? So if you again apply another convolution layer, now you have to specify the filter, the channel dimension is going to be 6 because your input has a channel dimension of 6, right? So this has to be carefully specified based on the input of the previous layer, okay? So yeah, I think we can stop here. Maybe we'll pick up the rest of the modules for the CNN for the next class. Hopefully, you can learn some of the basics. Then later, you're able to apply this knowledge when you, do the homework for medical image computing and reading some of the papers that using deep learning for medical image processing. Okay.